All right, so next we are going to have our first keynote speaker for the day, Rachel Rodinger. Rachel is an assistant professor in computer science in University of Maryland, College Park. She also holds joint appointment in the Department of Linguistics and the Institute for Advanced Computer Studies, AUMD. Her research focused on natural language understanding, including knowledge acquisition, common sense reasoning, and semantic representation and fairness in NLP. Without further ado, let's welcome Rachel.
Great. Thanks, everyone. It's great to be here today. I'm going to take just one moment to set up my slides. Okay, great. Hi, everyone. I'm Rachel Rudinger. I'm an assistant professor at the University of Maryland, College Park in the Computer Science Department, and it's my great pleasure to be here today. I remember back when I was a PhD student, MASC was the first conference that I presented at, so it's an honor to be back. And just one note for those of you coming from Hopkins, my apologies, you've probably seen some of this talk, but I promise there's some new stuff at the end. Okay, so my talk title is Not So Fast, Revisiting Assumptions in and About Natural Language Reasoning. So I'm going to start off with the question of what is natural language reasoning? So this is any of a variety of tasks that describe some kind of situation in natural language, such as somebody dropped a glass on the floor, paired with some kind of inference that one could make about that situation, such as the glass shattered. So in some versions of this task, we might apply a label, a discrete label like entailed, neutral, or contradicted, that indicates whether that inference is true given the context. So entailed means the inference is true given the context, contradicted, it's false, and neutral, we don't have enough information to decide. We could also label that inference on a more continuous scale of subjective likelihood judgments ranging from impossible to certain. And we can also have a generative version of this task where, given a description of a situation, we can automatically generate possible inferences about the situation. So that's the context for what I'm going to talk about today, reasoning in natural language. So the talk outline, I'm going to have 3 sections. And each will involve some aspect of assumptions in natural language reasoning systems or assumptions that we make about them. So the first section is about overriding assumptions with defeasible inference. So the idea here is that in certain kinds of situations, we might make an inference that is likely or plausibly true given the context, but given new information that we learn, we might then have to retract that inference. So if we drop a glass on the ground, we might infer that it's likely to have broken, but subsequently we learned that it fell on a soft carpet and we have to revise that inference. The second section, I'm going to be talking about revisiting assumptions that some of us as researchers have made about natural language reasoning systems based on the results of partial input baseline research. So partial input baselines have shown that natural language inference models can ignore the context description of a situation, but we're going to ask, do they actually ignore that context? And the third and final part of the talk will be about harmful assumptions that models make about people based on their social identity. So this is in assumptions in the form of social stereotyping. How does social identity influence the kinds of inferences that common sense reasoning models make? Okay, so moving on to part 1, overriding assumptions with defeasible inference. So first, what is defeasible inference? Here's a sort of classic example. We begin with a premise, Harold is a bird. We can make an inference from here that therefore Harold flies. But supposing we subsequently learn that Harold is in fact a penguin, more specifically, we then have to revise that inference that Harold flies and conclude instead that Harold does not fly. And so what does this word defeasible mean? The dictionary definition is capable of being annulled or made void. So when you hear the word defeasible, think of the word defeat, as in to defeat an argument. So I'm going to first make a quick argument that defeasible reasoning is ubiquitous across domains. In scientific reasoning, I like this quote, "The laws of nature are oaken, not iron." So the idea here is that all kinds of rules about how the natural world operates are subject to exceptions. So in general, mammals give live birth, except monotremes, which are a form of mammals that lay eggs. Newton's laws of physics, force equals mass times acceleration, is generally true, except when we're talking about systems traveling near the speed of light. Talking about physical common sense, this is everyday kinds of situations interacting with the physical world. We make all kinds of inferences of the form, if Pat drops a drinking glass, it will break when it lands. But as we saw, there's exceptions to that if it lands on something soft. Wet surfaces are slippery to walk on, but less so if you're wearing rubber-soled shoes. In the domain of social common sense, we're talking about reasoning about everyday social situations, people's motivations, what kinds of social norms govern social interactions. All of these rules are also subject to exception. They're a form of defeasible inference rules. So in some cultures, it's customary to shake hands as a greeting, but we've learned during a global pandemic that that may be less so the case. It's rude to not show up to a wedding that you agreed to attend, but it may be okay in various circumstances like illness. And there's a number of other kinds of examples of domains where defeasible reasoning is very applicable, including linguistic pragmatics, talking about implicatures, legal reasoning, the medical domain. It's just applicable all over the place. So now I'm going to talk about sort of the more applied version of this task that we're going to talk about today. So we're going to start with this observation that most natural language inference data sets are of the form of context inference pairs. So we have some description of a situation, that's a context, we might also call it a premise, paired with an inference. So here the context is someone dropped a drinking glass, the inference, the glass shattered. And what this lacks is the kind of additional context that one might want to know that might shape how likely this inference is to be true or not. So for example, as we saw, if it falls on something soft, that inference is less likely to be true if the object was dropped only an inch from the ground, or it's made of durable glass, or the situation is taking place on the moon. All of these additional pieces of information would weaken that inference. And conversely, if we learned that the glass was made out of a very thin glass, or if it's dropped off from a very high height, or it lands on something hard, this would make us more likely to believe that this inference is true. So this is something that is often lacking in the kind of one-off context inference pair style of natural language inference data set. So this is exactly what we're going to be focusing on here, is extending existing natural language inference data sets with these kinds of additional context that makes an inference more or less likely to be true. And this is work with a bunch of fine folks at AI2 and the University of Washington. So we introduced this task called defeasible natural language inference. The task definition here is very much inspired by the task definitions of natural language inference and recognizing textual entailment, if you're familiar with those. So given a premise P, we'll say that a hypothesis H is defeasible if there exists an update sentence U, which has to be consistent with the premise, such that a human would find H less likely to be true after learning U. So now we're going to call an update U a weakener if a human would most likely find H less likely to be true after learning U. And instead, if they would find H more likely to be true after learning U, then we'll call U a strengthener. So we created this defeasible NLI dataset called delta NLI for short. To demonstrate that it's applicable across a number of different domains, we extended a variety of natural language inference data sets, including the Stanford Natural Language Inference dataset, the Atomic dataset for common sense inference, and the Social Chemistry 101 dataset for social common sense. And so each of the corresponding extended versions of this dataset are going to be called delta SNLI, delta Atomic, and delta Social, respectively. Okay, so how do we collect this data? How do we augment these data sets? So we're going to start with the context inference pair from the original data set. We'll present it to a crowdsource worker, and we'll ask them to write one strengthener and one weakener. So with our recurring example of the shattering glass, they'll write the weakener about it falling onto a pile of laundry and a strengthener about it landing on concrete. So after doing this process, we've collected about 100,000 examples for delta SNLI and delta social, and about 50,000 for delta atomic, with a roughly 50-50 split between strengtheners and weakeners after going through a validation process. So I'm going to show some examples of the kinds of data that we collected from this process. So first, the defeasible SNLI set. So we've got an original example from SNLI. The premise, 2 men and a dog are standing among rolling green hills. The hypothesis, the men are farmers. And note that this is a neutral inference. We don't know for sure if this hypothesis is true or false. There's not enough information to tell. And only neutral hypotheses can we apply strengtheners or weakeners to. If it was an entailment or a strict contradiction, we wouldn't really be able to modulate the likelihood of it being true just by adding new information. So in this example, the weakener that the annotator wrote is the 2 men are wearing hiking backpacks. So this tends to suggest that the 2 men are, in fact, travelers rather than farmers. And the strengthener that they wrote is the dog is a sheepdog, which is kind of generally suggestive of a more pastoral or agricultural scene. Okay. In the second example of the extension of atomic, so atomic is a data set for common sense reasoning. It involves brief descriptions of a scenario involving a generic person called person X, paired with a whole bunch of different inferences about that situation along different inferential dimensions, such as what happens next, what caused it, how do other people feel about it, and so forth. And so what we're going to do is we're going to take the original description of a situation, person X is sprayed by a skunk in this case, and we're just going to take one branch of these branching inferences at a time. So in this example, as a result, person X feels smelly. We'll treat that inference as the inference. So now we've got a context inference pair. And the weakener that the annotator wrote for this example is person X is wearing a protective smock that might tend to prevent them from becoming smelly after being sprayed by a skunk. And the strengthener is many people are pinching their noses around person X. That would be a form of evidence that they are, in fact, smelly after being sprayed. Okay. And then finally, example 3 for defeasible social rules. So the Social Chemistry 101 data set contains statements of general social rules, such as it's okay if you don't like the food someone gives you and don't want to eat it. These are crowdsourced. And note these are not context inference pairs. It's not 2 separate sentences, but rather there's kind of an implicit if-then structure to these generic rules. So now the weakener in this case is something like, unless you told them you would try some, and the strengthener is especially if you're allergic to. So it's especially okay to not try the food if you're allergic to it. Okay, so we created a classification task out of this data, given a premise, hypothesis, update tuple, predict whether or not that update is a strengthener or a weakener. And the majority class baseline should only perform at about 50% here, and a fine-tuned Roberta model with the full input performs at about the 80% level. And what we noticed is, perhaps not that unsurprisingly, when we train partial input models by first removing the premise from the context and then removing both the premise and the hypothesis, we see some degradation of performance, but to varying degrees. So removing the premise doesn't greatly harm performance, and this kind of makes sense if you think back to the penguin example, where that update sentence is Harold is a penguin. Well, that example actually entails the original premise. So once we know that Harold is a penguin, we don't really need to know that Harold is a bird. So in some cases, that original premise isn't as useful. Removing both the premise and the hypothesis does significantly degrade performance, but the performance is still above a majority class baseline. And so we see that there are, in fact, based on the protocol that we're using here, some amount of artifacts that have been included in this. So we're going to move from a classification framework to a generation framework. And we're going to ask, given a premise hypothesis pair, can a model fine-tuned on this data generate strengtheners and weakeners? And we find that in many cases that a fine-tuned, at the time this was a GPT-2 model, is able to adequately generate some reasonably good strengtheners and weakeners. So in this example, a surfer is riding the waves whilst another surfer sits on his board waiting. The hypothesis is the people are surfing in a competition. So we've got a strengthener that the model generates. The people are wearing numbered bibs. There are judges watching the surfers. These all indicate that we're more likely to be in a competition scenario, whereas the weakeners, the surfer on the board looks bored, the surfer on the board is a beginner, tend to undermine the idea that this is a competition. In social chemistry, the generated examples for this social rule, it's wrong to ditch your friends. The strengtheners are they need your help. They're stranded in the middle of nowhere. These are both sort of intensifiers for this particular social rule. And on the other hand, if your friends are taking advantage of you, you have to go to the hospital, then this social rule seems less likely to apply. And these are examples that the model was successfully able to generate. Okay, so in general, what we observed about the quality of the generated strengtheners and weakeners are they're topical and fluent. That's a good thing. Many effective strengtheners and weakeners are created. And this is something that's difficult to do accidentally. So it's clearly learning something from the data. The bad news is some of the generated strengtheners were sometimes swapped. And sometimes we observed that weakeners contradict the premise or strengtheners would presuppose or reiterate the hypothesis, each of which are kind of against the task formulation that we gave to crowdsource workers in the original generation task, or the original elicitation task. And then we have these kind of broader questions about when models are sort of defaulting to these broad purpose weakeners, which is one behavior that we observed. So in the case of social reasoning, we see things like, the other people are mean. That's kind of a general purpose weakener that overrides a lot of social rules in many different situations. What do we make of this sort of backing off, defaulting to broader purpose, less targeted update sentences? That's one question. And another more open question here is how well are we actually able to cover the possible space of strengtheners and weakeners? And this is going to still be a very interesting question going forward, even with much more powerful generative language models that we have in just the past few months. Okay, so now we have this question. Are the models actually learning to do reasoning from the data, or is that partial input baseline performance that we saw, does that kind of call this all into question? Could we say, well, they're not really learning to do reasoning because they can get, 60, 70% accuracy just on the update alone without even looking at the premise and hypothesis? But we see, on the other hand, that generative models are capable of learning to generate valid strengtheners and weakeners from the data. So clearly, something must be learnable from the data that we've got here. So what's going on? And that's going to lead us to part 2, where we're going to talk about revisiting an assumption that some of us as researchers have made about partial input baselines and what they tell us about the reasoning capabilities of these models. So this is work by my PhD student, Neha Srikanth, who's here today. So and she's got a poster, so you should go talk to her about this if you're curious. This work is about the partial input baselines that we saw coming out a few years ago. I was involved in some of that work, as were a few other groups around the same time, observing that in the natural language inference task, if you occlude the premise, if you just remove it from the input, you're still capable of getting a prediction accuracy much above what you would expect at random. So we would ideally want an NLI model to be taking advantage of both the premise and the hypothesis in making a prediction about whether the hypothesis is entailed or not. But we actually find is that in a lot of cases it doesn't have to use the premise in order to do reasonably well. And so what does this mean for the reasoning abilities of these models? Okay, so there are, broadly speaking, a couple kinds of inferences that we could make about the reasoning capabilities of these models in light of the partial input results that we've seen. So the first conclusion that we could draw here is that hypothesis-only baselines, so hypothesis only being that we're only conditioning the prediction, the NLI prediction based on the hypothesis or the inference without respect to the premise. Hypothesis-only baselines are learning to leverage dataset artifacts that hint at the correct answer and thus are able to make correct predictions without actually doing reasoning, because they're not actually measuring anything about the relationship between the premise and the hypothesis. So that's one conclusion that we could take away here. The second is that full input models must therefore be doing the same thing. So a full input model taking both the premise and the hypothesis then are just making the same kind of inferences that a hypothesis-only model is making. It's exploiting these data set artifacts rather than learning to reason. And this would not be a good thing. Okay, so we're going to actually take a look at this second conclusion and ask, is this a valid conclusion? And to start, I'm going to make an analogy here to a math test. So imagine we've got a multiple choice math test, and we give a bunch of practice tests to a student to go study for this test, but we've removed the questions. So all the student can see is the multiple choice answers, A, B, C, or D, and they can sort of maybe find some patterns like answer B is more likely correct than answer C. Even numbers are more likely to be the correct answer than odd numbers. So they can find these sort of patterns, and they come back and they get a 65% on the test. Meanwhile, we give the same tests to another student where we don't remove the math question, and we allow them to study the tests to prepare for the test, and they come back and they get a 92%. They do much better. And what might be going on here is that even though there are little hints in the answer, maybe B is slightly more likely to be correct than C and so forth, at the end of the day, what's actually a more effective approach for getting high performance is to actually just do the math problem. That's the most reliable way to answer the question correctly. So the second student just learns to answer the question correctly by actually doing the math problem. And so that's the question here. By analogy, do full input NLI models with access to both premise and hypothesis learn to condition on the premise despite being trained on data sets that contain these artifacts? Okay, so our central question, do NLI models learn to condition on, now we're going to call the premise, we're going to relabel that as context, and you'll see why in a moment, despite being trained on data sets containing artifacts. So we're going to run some experiments on 2 NLI tasks, the original Stanford Natural Language Inference dataset, as well as our defeasible version of that dataset. And so now we're going to talk about a context and a target. So in SNLI, the premise sentence is what we'll call the context, and the target sentence is the hypothesis. And in the case of defeasible NLI or delta NLI, we'll call the context, we'll call the premise and the hypothesis collectively the context, and the target is the update. And so now our partial input models for each of these 2 tasks will receive only the target, either the hypothesis or the update alone. And the full input model will receive both context and target. Okay, so one thing to note is that conditioning on context would not necessarily be a sufficient condition for us to conclude that these models are actually reasoning, but it would be a sufficient condition for us to invalidate conclusion 2, that conclusion that we're looking into as to whether do full input models just do the same thing as partial input models. Okay, so we're going to now investigate the role of context in NLI models through 2 sets of experiments. The first experiment is about context in NLI. Does access to context strengthen a full input model's confidence in the correct label compared to the partial input model? So we're going to be looking at whether the model's confidence in the correct label increases when it receives both the context and the target as opposed to just the target alone. And the answer is yes. Full input models are, in fact, more confident in the correct label than their partial input counterparts. And the second experiment is going to involve editing the context. So we're going to ask, are full input models sensitive to changes in the context when artifacts are present in the target? And the answer there will also be yes. We will show that full input models are, in fact, sensitive to context modifications even when there are artifacts present in the target. Okay, so experiment 1, we are going to show that access to context strengthens a full input model's confidence in the correct label compared to the partial input model's confidence. And so this plot here is showing each dot on this plot is one test example from SNLI. And we're looking at, on the x-axis, what is the confidence of a partial input model? What's the probability that a partial input model assigns to the correct answer? So that ranges from 0 to 1. And on the y-axis, we see what is the, for that same problem, what is the probability or confidence assigned to the correct answer from the full input model. And what we're seeing here is that, so any dot that lies above this red dotted diagonal, above the y equals x line, is a case where the full input model had a higher confidence in the right answer than a partial input model. And we see that the vast majority of the density lies above that dotted line. So what this is telling us is that in most cases, adding in context is allowing the model to become more confident in the right answer. And similarly, we ran a same set of experiments, but for the defeasible NLI task. This is only a binary classification task. So you can see on the right-hand side, those are all of the cases that the partial input model gets right, and the top half are all of the examples that the full input model gets correct. And again, we see that most of the density lies above that diagonal. So in both cases, adding in context is allowing the model, the full input model, to be more confident in the right answer than the partial input model. Okay, so experiment 2, we're going to ask, are full input models sensitive to context modifications that actually flip the label? And so in this case, we're going to take an example, a premise-hypothesis pair, where we're reasonably confident that an artifact is present in the hypothesis because a hypothesis-only model has made the correct prediction. But now we're going to try to trick the model by editing the premise, making a slight modification so that now the correct label for the edited premise along with the original hypothesis is different from what the original label is. And now the question is, despite the fact that an artifact or some kind of clue is present in the hypothesis pointing to one label, is the model able to switch to another label when we modify that context? And what we find is that in the majority of cases, the trained models do pretty well at flipping their labels. So this is a breakdown of all of the different possible original labels mapping to the new label. And in most cases, we're seeing relatively high accuracy. The only counter case here is when we're trying to flip a neutral label to an entailed label. In that case, the accuracy is somewhat lower. So the model shows a lower ability to flip the label in that case, but overall, a relatively high ability. And then for the defeasible task, we're looking at cases where the model has to flip the label from a strengthener to a weakener or vice versa. And in general, we see pretty high performance in both of those cases. So the key takeaways here are, first, it's hasty to conclude that models trained on data sets with artifacts are not capable of reasoning, even though high-scoring partial input baselines show that full input models could ignore context. These experiments are showing that they don't do that. They can actually leverage the context very effectively. Second, artifacts can and do lead to models with exploitable heuristics, but artifacts don't necessarily spell disaster for a model's reasoning capabilities. Thirdly, NLI models can and do meet one of the necessary conditions for reasoning, that is, leveraging the full context or the full input. This isn't, as we said, a sufficient condition, but it is inherently necessary. And finally, partial input baselines should be understood as a sort of warning sign. So they're sufficient to conclude that partial input models might not be leveraging critical context, but insufficient to prove that they don't. Okay, so moving on to the third and final part of this talk, now I'm going to be talking about assumptions that models make about people that are harmful because they encode various kinds of harmful social stereotypes. So making inferences about people based on gender, race, ethnicity, and so forth. And this is work with my PhD student, Haojia An, another UMD student, Zhongxia Li, as well as Jieyu Zhao. Okay, so this work is called Soda Pop. We're developing a system called Social Bias Discovery from Answers About People. And the context here is we're talking about social common sense reasoning tasks. So this is a form of a natural language reasoning task where our context is a description of a situation involving people engaged in some kind of activity, and the questions that we have to answer about that situation, the inferences that we have to make, are about the people involved in those situations. So as an example, this is the social IQA dataset by Martin Sapp et al. And the context here is a person regarded every person carefully before they decided whom to talk to. How would you describe that person? And so we've got 3 multiple choice answers. Answer A, a cunning, ruthless predator. Answer B, one funny, intelligent person. Or answer C, a nervous, calculated person. And in this case, the correct answer, according to the data set, is a nervous, calculated person. And so one thing to note here is that it really doesn't matter what name is. We can answer this question regardless of what name we swap in. It doesn't depend on the name. It just depends on the surrounding context describing that situation. Okay, so then as a result, it's a little bit concerning that when we see on this example, and this is a real example, if we swap in the name Aisha, which is commonly an African-American female name, into the name slot, the model predicts answer A, a cunning, ruthless predator. And in the second case, if we swap in the name Nancy, which is more commonly a European-American female name, the model instead predicts answer B, one funny, intelligent person. So we don't think that the model should be changing its answer based on names. And furthermore, the way in which the model is modifying its answers are reinforcing harmful social stereotypes about people based on race and gender. Okay, so what we're going to do here is run a number of name substitution experiments. So we're going to counterfactually modify these examples by swapping in a whole bunch of different names that we have associated gender and race ethnicity statistics for. And we're also going to generate a whole bunch of different possible distractor answers by taking the correct answer and modifying it one word at a time using a masked language model. Okay, so now we're going to have a whole bunch of modified examples from which we can now start to look at this not just one case at a time, but in aggregate. What's the sort of overall aggregate statistical behavior? Okay, so how likely is a distractor to fool the model? That's the question we're asking. And as we see, it's going to depend on the name and the associated demographics of that name. Okay, so we're going to define this measure called a success rate, which is a function of an individual word that appears in the distractor as well as the name. So the success rate is defined as the probability that the model chooses a distractor over the correct answer, conditioned that the word W appears in the distractor and the name N appears in the context. So now for a given name, we can, and a vocabulary of words, we can define a success rate vector of success rates for that name and a bunch of different words. So each component in that success rate vector will be the success rate of that name with a particular word. So now we can create a success rate vector for every single name that we're studying. And when we take all of these names and just for visualization purposes, apply a two-dimensional t-SNE projection, we can see that these success rate vectors are clustering very strongly based on the demographic attributes of the name that the success rate vector is based on. So in this graph over here, we can see a cluster of each of these dots represents the success rate vector for one European American male name. These red dots, this cluster shows African American male names, and we can see that the success rate vectors are very clearly encoding information about race and gender, even though we're not actually inserting the name or any explicit information about demographics into the success rate vector. The success rate vector is defined purely in terms of the behavior of the model. So now we can recover this demographic information. So we think that the more recoverable this demographic information is from these success rate vectors, the greater the degree of bias present in the model. So we performed an unsupervised k-means clustering task, just a two-way clustering. And so what we would hope to see, if that information wasn't present at all, if all names for this task were being treated in the same way by the model, these should be indistinguishable. The accuracy should be close to 50%. And what we're seeing is the accuracy is much, much higher. And even more concerningly, when we use supposedly debiased versions of the language model that we're fine-tuning this task on, or if we apply debiasing methods before or after, we still find that the classification accuracy is quite high. And so this is really indicating that demographic information is coming through loud and clear in the behavior of the model, even despite efforts to debias. Okay, so now qualitatively, we want to look at what are the actual kinds of stereotypes that this approach is detecting. So we're going to compare here the words that are most strongly associated by the model, the words with the highest success rate vectors for female African American names versus female European American names relative to one another. And we see that the words most strongly associated with female African American names are words like stubborn, brutal, vicious, violent. We see a lot of words encoding known negative, harmful social stereotypes about African American women. On the other hand, we see words that are just falling out of this algorithm for female European American names that have overall much more positive sentiment, caring, educated, sweet, sophisticated. We see associations with class. We see associations. We also see some stereotypically female attributes as well. And so we can see that the model is behaving in such a way that is not only making different predictions about the people involved in these situations, but also in ways that reinforce existing harmful, negative stereotypes about people based on race and gender. One thing I'll point out is that although we're able to see a lot of interpretable stereotypes that come out that align with known harmful stereotypes, a number of words or attributes come out that don't have as obvious an explanation, but yet these are still attributes that the model is, in a statistically significant fashion, associating with one group or another. And so the sort of typical approach for studying bias in natural language processing or AI is to start out with a predefined social stereotype and go search for it in an AI system. But it could be the case that there are other kinds of disparate behavior that these models are exhibiting that don't necessarily align with known or well understood social stereotypes. And this could be a method to discover those. And I think a very interesting path for future research will be to kind of try to understand where these not easily aligned to known human stereotypes are coming from, and what we should do about them. Okay, so that's the main content of my talk. The main takeaways here are, so we talked about 3 different kinds of assumptions in or about natural language reasoning systems. First, we talked about assumptions that can be overridden in the case of defeasible reasoning, and this defeasible reasoning framework offers us an approach to better context-sensitive reasoning with potentially broad applications. In the second part, we talked about assumptions that we've made, or some of us have made, about the meaning of partial input baselines, and we've revisited that to conclude that the results of partial input baselines should be understood as a red flag rather than a final verdict. And finally, we have looked at the kinds of harmful assumptions that natural language reasoning models, particularly in the case of social common sense reasoning, make about people based on demographic attributes. And we've shown that name substitution can be a powerful method for automatically uncovering various types of stereotypes. So that's all I've got. I'm happy to take any questions. Thank you. In the back? So made up names like that are not known to be, can you give an example?
Okay. Yeah, so I don't know, like something out of Dr. Seuss or something?
Oh, I see. Yeah, that's a great question. We didn't run that experiment. That would be an interesting one to run. What we did do is we ran various kinds of bootstrapping statistical significance tests to make sure that if we, for example, randomly relabeled the associated demographic attributes on the names that we were using, that the effect sizes that we were observing were then, it's not just random coincidence that we get this different behavior. It really depends on the correct labels, the correct demographic attributes. But that would be a really interesting experiment to run as a sort of counterfactual.
Okay, yeah, sounds good. Thanks.
In the front, hi.
So in the third part, did you try to add besides just doing name substitution, did you try to add some description for that name? For example, like Alicia is an African American woman, and then in that way it can further elicits model hidden knowledge?
Yeah, that's a great question. So for soda pop in particular, oh, yes. So the question is, did we use, besides name substitution, do we use other kinds of descriptors of people like the African American woman or other kinds of phrases that might directly or indirectly convey demographic information besides just the name? So for soda pop, we didn't do that, but I have other work that looks exactly at that kind of question, in particular in generative common sense reasoning tasks. So we take a situation, a basic description of a situation, like a person earns money, and we substitute in fact, I have the slides for it, but I don't know if I have the time to show it, but happy to talk more about it afterwards. We take a situation description, like a person earns money, and we swap in different descriptors of that person. So an African-American person earns money, a woman earns money, a man earns money, and we also used not just gender and race and ethnicity, but also nationality, socioeconomic status, so all kinds of descriptors of different classes of people, and we find that perhaps unsurprisingly, that the generative inference models are strongly influenced by the information about the person. So we actually looked at are the inferences influenced by the context? Are they influenced by the identity of the person, or by both? And for certain classes, we find that the influences are very strongly influenced only by the identity of the person. So we've done that in other kinds of experiments. But in general, it's a very good question of how do we actually, for scientific purposes, when we're trying to audit these models or trying to understand their behavior, what are the different ways that we can represent demographic attributes? And names are only one way of doing that, yeah. Oh, in the blue plaid? I saw your hand. Yeah. Oh.
There you go. Thank you for your talk. Very interesting. For the name, the last part, you mentioned that you tried to debias the models and that it didn't work. I was wondering what
kind of debiasing methods did you use? Were there like internal or external? I know that prior work has shown that they don't kind of correlate.
Yeah. So my student, Hauja, who is the one running these experiments, used a variety of sort of out-of-the-box debiasing methods, and what we found, what we did was we actually also ran these counterfactual augmentation experiments where we gave the model a single example. With a single example, we gave the model many training instances with different names substituted in with the same correct answer. So we were kind of hoping that it would learn to be indifferent, but that wasn't the case. That the fact that it's fine-tuned on top of large language models, somehow that information still carries through. We haven't tried more sophisticated. This is not to say that there couldn't be a method of debiasing that's a little bit stronger that actually does the trick, but sort of the out-of-the-box methods and the simplest counterfactual augmentation methods didn't seem to work here.
Thank you for the talk. So my question is like a little bit follow-up to the previous question. So do you have any idea like what kind of debiasing methods may help to reduce these biases in the models?
Oh, yeah. So this is something that we'll probably be looking at in sort of upcoming work, is how to more actively debias the models. At the very least, for this particular task, there's really no reason that the models should be dependent on the names. And so rather than just creating counterfactual examples, we could also try to more actively penalize the model for having divergent behavior on examples that have different names. So we can use some various forms of regularizers or other components of the learning cost function, and that's sort of where we're going next.
Thank you so much for the talk. So my question had to do with some of the work on natural language inference. And I guess I was just wondering to what extent you can use this work that talks a lot about what these models are doing and potentially extend them to determine like what are the algorithms behind reasoning with language in general and generating pragmatic inferences.
So in terms of how can we generate pragmatic inferences, this is something that we're looking into. Neha and Rupak, I see right here, this is exactly what we're talking about right now, is looking at, given some context or given a question, can we sort of automatically understand what the defeasible inferences are, so the pragmatic inferences, the implicatures, those kinds of inferences that are generally thought to be soft inferences, cancelable inferences based on context or things like Gricean maxims of cooperative conversation. That's exactly another thing that we're interested in here. And I think using the defeasible framework is useful in terms of thinking about the cancelability of implicatures often involves thinking about, okay, what contexts would override or cancel this implicature? We could think about generating the context, in the sense that we have generated strengtheners and weakeners here. Perhaps we could apply this instead towards pragmatic implicature and try to generate, well, what context would this pragmatic implicature no longer hold under? So I think there's a tight connection there, yes.
Thank you.
All right, let's take one more last quick question, just because time constraint. So, okay.
Hi, sorry, it's a really quick question. I just wanted to know what is the source of your data, where the instances come from?
For which part?
for this one here? Just mainly, I think you mentioned it earlier on. I might have missed it.
Oh, okay. So this is the social IQA data set by Martin Sapp et al. And the source of, in order to create the counterfactually augmented examples, we use names from a variety of sources. There's, I'm forgetting the citation, but it's in the paper. We used some sources that have actual real-world statistics associated with the names. We weren't asking annotators to sort of predict anything about the demographic attributes of a name. It's actually from census data or Social Security data, or I think one of the data sets is births in New York City from a certain time range. And the associated demographic information for those names. So it's based on real-world data.
That's perfect. Thank you.
All right, let's thank you, Rachel, again, and moving on to next section.